Oh, now we're recording. So the Earth's crust, the outer part where the continents and the ocean floors are, it's composed of a number of plates that are independent and broken apart from each other, as you can see on this map. And as the red arrows indicate, the plates are not static; they are moving relative to each other. In some parts, they are moving away from each other. Normally in the ocean floors, you can see that. But in some parts, they are moving towards each other and colliding. That is the case, for example, in South America, in Chile, here, in Japan, over here. And it is this movement that gives the energy necessary for earthquakes to happen. Okay. What fuels this movement, or what makes these gigantic plates move, it's actually not very clear. Like, geologists still fight about it, but it's, for our purposes, it's not very important. We just need to know that they move, that this movement caused the earthquake, and the more movement we have, the higher the risk of an earthquake, and the higher the intensity of the earthquakes. If we compare this map of the plates with this other map, where you can on this side still see the plate boundaries, and in this side you can see the earthquakes that have been measured in a period of around 30 years. And you can see that they are in very well-defined zones, and always, or almost always, around these plates and their movements. And there are some earthquakes in the ocean where the plates are moving away from each other, but the earthquakes are mainly concentrated in areas where the plates are moving towards each other, around the Pacific Ring, and also between the Africa and European plate. So what happens when two plates collide? It's that one of them is almost always heavier than the other. So when they collide, the heavy one tends to sink under the lighter one, which kind of, in this case, floats up above the heavy one. And because the movement of the heavy one is pushing against it, is trying to compress it. Normally, this process creates mountains. This compression of the plate. That is why earthquakes are more common in mountainous region, whether it be in South America, in Japan, or in Southern Europe, for example. And of course, this process is not frictionless. We're talking about millions and millions of tons of rocks, entire continents moving to each other, and where they do contact, there is a lot of friction. So they don't simply slide against each other, right? When the oceanic crust moves, it wants to drag with it the continental crust also, so that this continental crust bends. Okay, originally it was straight, but because it's trying to follow the oceanic crust downwards, it bends. And all this energy is stored in the continental crust as elastic energy. So if you imagine the continent to be a gigantic beam, that it's being bent by the force of this friction, well, it's the same process. But at some point, the friction in this point will not be enough. So the forces involved will be too large, and the friction will be overcome. And then this beam will release, and it will spring back to its original shape, or to its undeformed shape. And that will create the earthquake. It is this jumping or this very sudden unloading of this bending force that, of course, creates this shaking that we will see in any elastic material, in any kind of beam or spring. But in this case, it's like at a planetary level. Okay. So I want to show you a little bit. There are probably several of you who are from countries that are seismically active, that have earthquakes, but I am from Chile, one of the most seismic active countries in the world, and I was in Chile in 2010 for what back then was the 6th largest earthquake recorded in history. So I wanted to show you a few pictures of that earthquake, so that you can get an idea of the magnitude of these events and the destruction they can cause, and also the engineering challenges that need to be overcome. This was a bridge, for example, in a city called Concepcion, very close to the epicenter. Yeah, and the city is like many cities on a river, and there are 3 bridges crossing the river, and all 3 collapsed. So the city was entirely like separated in 2 halves, and there was no viable road to cross it for many, many weeks because of the earthquake. This was a very old bridge. But still, you could see that almost every single pier collapsed, and of course the deck on top collapsed when the pier collapsed. This is a building in Santiago, which is the city which I was at the time. And you could think that this building doesn't look all that bad, but there used to be a floor here that now is completely gone. So that floor disappeared, and the building simply popped down one entire floor. So there was probably sheer failure of the pillars of this floor, so that the entire building sank down 1 floor. Believe it or not, that building is still standing today and it's being used. What the owners did is they removed all of this, all of this part. So now only the lower, I think 10 floors or something of the bridge of the building are still standing, and they are used. It's offices, a building for offices. Yeah, I don't know if I would like to work there. It's probably after receiving an impact of 7 or 8 floors, probably not the safest building. But at the same time, all this was designed to be much stronger than it needs to be, because all this has been removed, which anyhow, that's just anecdotal. This is another building that fell down entirely. So it just fell flat on its back, you could say. These two buildings, the previous one that I showed you and this one that you're seeing now, they were both empty because they were new. They were newly built and they haven't really been finished, so there was no one living there. And that is one, I guess you could call it advantage with seismic region, that the buildings that fall are always new ones, because in Chile, at least, we have an earthquake of magnitude 8 or more every 10 years. So any building that is older than 10 years has already survived one earthquake like this. So there were very few deaths in this earthquake in Chile, actually, even though several buildings failed, but they were all new buildings. They were all empty, and they were all later being studied for corruption and falsifying of the safety permits and all that. Because, I mean, this is not normal. There were like maybe 6 or 7 buildings that collapsed, but no, the country more or less continued to work. There were much more people there that died in traffic accidents during the earthquake than because of bridge collapse, or building collapse. This is a church close to where I was living also, or what's left of it. And of course, the building was also, the earthquake came also with a tsunami. So you can see some boats out of place that were pushed up by the waters. Here you can see that the city, even though there was a tsunami and there was lots of flooding, but the buildings are more or less all standing where they should be. Here we have another view of the city of Concepcion. And this is a interesting image. What we're seeing here is the GPS measurement for a number of cities, okay, in Chile. And I was telling you this one here is the one in Concepcion, and the city where I was showing you the pictures from, and the city that was closest to the epicenter. Okay, here, and as I told you, if this is South America, sorry, and here we have the Pacific Ocean. The Pacific Ocean, it's moving towards the east, but South America is moving towards the west. So at some point during their movement, and they move, by the way, at the same speed that your nails grow. So that is the speed at which these continents are moving, the same speed that the human nail grow, which is not very fast, but of course, during the years it accumulates. If you never cut your nails for 10 years, you will have very long nails. So the continents can move quite a bit as the years go by, but they get stuck. So even though most of the continent is still pushing to move, because of friction, it gets stuck on the plate going the other way, and its movement, its stop, and all that energy goes into compressing the entire mass of the continent. And when they release, we get this very sudden movement, and that's what we can see here. So the lower, as you can see, the x-axis is in seconds, and the y-axis is not being, the y-axis is in meters, right? So you can see that the entire city of Concepcion jumped something like 6 or 7 meters to the west in a matter of, yeah, maybe 10 or 20 seconds. And that is because of this phenomenon that we have here, right? The continent was trying to move west, but was being stopped by the friction of the ocean floor below it. But once that friction released, then all that movement is actualized. So that every single coordinate in the GPS, every street, every house, every address was off by several meters after this earthquake. Of course, yeah, everything can be recalibrated, but this is like measurable effect of the earthquake. Yeah, and some information about the earthquake. It had a maximum acceleration of 0.6 or 0.7 Gs sideways, right? So of course, if you have a building and you design each column to support the weight of the structure and maybe, I don't know, a couple of meganewtons, it's not unusual for a column to support a couple of meganewtons, then the column should be designed to support 60% of that mass or over that force in a sideways direction. Of course, a column can be very, very strong in its axial direction, but when you're designing for earthquake, then you have forces in this direction. And it's very hard to get a structure that is so stiff or that at least can withstand without collapsing those level of forces. And of course, it created a huge blackout because a lot of infrastructure failed. There was no electricity, you couldn't call. Cell towers were not working, and created a lot of damage. All right, so that is what an earthquake can look like. How do we measure earthquake? Well, nowadays, thanks to GPS and piezoelectric accelerometers, it is very easy to register an earthquake. There are stations that measure their location with the GPS very accurately, sub-millimeter accuracy, so they can track the movement of the Earth very accurately. And we also have accelerometers, right? The same kind of accelerometers that you have in your phones and your computer, but they are dedicated to measuring these vibrations. Up until the maybe 80s, earthquakes were measured by a seismograph, which is actually just like a pen on a long rod, which was placed on a pivot and with a spring, right? So if the, and with a mass here, this is the mass. So if the earth shakes, then the pen shakes, and they put some paper here. So the pen will draw the shape of the earthquake on the paper. And that was used for hundreds of years, but now it's all electronic, of course. And the earthquakes are classified nowadays according to two scales. The Richter scale, which is the old version of the scale, which is not really used anymore in scientific literature, but it's what you hear in the news when they say the degrees of the severity of the earthquake. And in scientific paper and people who study seismology, nowadays they use something called the seismic moment scale, which is slightly different. I see now that there is a question in the chat about how can some cities go back, like they kind of bounce back. So if we go back to this, the answer is that first we need to notice that the y-axis is not the same for every city, right? Okay, they are measured meters, but there are different magnitudes. So we had Concepcion, the city close to the epicenter, where the city moves 7 meters or something like that. While these other cities that bounce back, if we take, for example, this one, the movement is under a meter, right? It moved a maximum of 0.7 meters. And then it went back to maybe 0.2 meters, like this line here. It's 0.2 meters. So what is happening there is a wave, okay? We have the Earth, the Latin America, South America moving in this direction, and then this ends get stuck on the ocean floor, so it starts to bend, and then it releases. And when it releases, this point, the point that was stuck, moves a lot, of course. But these other cities are very far away from the point that moved the most. So if now we have Chile or Latin America in this, looking from up, if this point gets very violently kicked, then all the other points will just feel a wave. But once that wave passes, then they will not have moved so much. So that is why all these other cities, here, they kind of kick back, because they were farther away from the epicenter, and what you're seeing there is the wave passing by. Yeah. I hope that answers the question. Okay, as we were talking, the Earth is elastic, right? It has a stiffness and it has a mass, so it vibrates. And these vibrations propagate in the form of waves. And when it comes to seismic waves, or well, any kind of waves really, but particularly in earthquakes, we have two types of waves. Well, actually many types, but they can be classified into two different classes. One is body waves and the other is surface waves, okay? Body waves are waves that travel through the inner part of anything, right? So sound, for example, is a body wave because it travels through air. It doesn't need any other medium, and it travels right through the air. You can have sound through water also, of course, or any material. But the important thing is that it travels in the inside of the material. So when I speak, my mouth and my vocal fold is compressing a little bit of the air here, but that air that I just compressed, it wants to expand, but when it expands, it pushes on the next bit of air over here, and it compresses it, but that in each time also wants to expand back to its normal volume, but when it expands back, it pushes on this bit and compresses it. And so this wave travels through the air. And you can do that with any elastic material. If you hit it on one side, it will compress it a little bit, and when it expands back, it's going to move to the next beat and the next beat and the next beat and the next beat and the next beat. So, and that is a body wave. And the other kind of wave is the surface wave. And that is the kind of waves that you can see in the ocean. If you've ever been scuba diving, or if you ever like watch like a documentary, the waves in the ocean are only in the surface. If you dive down 1 meter or 2 meters even, the water is perfectly still. Because for this type of waves, surface waves, they can only travel in the interface between two mediums. You have the air, the water below in this case, and the air above. And that interface can create the condition for a surface wave. And they do not extend very deep into the material, all right? If we continue, we can further classify the P waves into two different kind of waves. Sorry, the body waves into two different kind of waves, the P wave and the S wave. P is called P for primary and S for secondary, okay? And there are many types of surface waves, many different types. The main ones are Rayleigh waves and Love waves, okay? The ocean waves are the most similar to Rayleigh wave that you can get. So I'm going to go into a little bit of detail talking about each one of them now. Okay. The primary waves. They are called primary because they are the first one to arrive, okay? So different kind of waves have different speeds at which they transmit, okay? So we're all used to the fact that the speed of sound is something like 320 meters per second in air. But of course, the speed of sound, which is a primary wave, depends on the material. It's completely different in water. It's completely different in steel. But they are the fastest of the possible waves. As I explained before, they are transmitted by this compression and dilation process. And the material in this case, the Earth crust moves in the direction in which the wave is propagating. So if the wave is propagating in that direction, then the materials are shaking back and forth also in that direction, okay? These waves can travel through any type of material, and they are not very destructive. That is because the rock or the continental crust that forms our ground, it is stiff. It is very stiff. So the compressions that the earthquake can achieve are small. They are like sub-millimeter. They are measurable and they contain a lot of energy, but they are of low in amplitude, right? So it's not very destructive. There are many accounts, for example, of animals sensing earthquakes before they arrive. And yeah, so the main theory is that they're probably hearing these waves, right? They're hearing these waves arriving, the primary waves, which are the first one because they're the fastest, and they get scared. And we don't feel them and we don't notice them because they are very small. And after the P waves, normally a few seconds after the P waves, the S waves arrive, the secondary waves. And they are transverse or shear waves. So if this piece of, if we have like imagine a beam here, if I pull this one up, because of the elasticity of the beam, it's gonna want to go back down. But while it's up, it's gonna pull the next bit up, and then it will go down. And now this bit is gonna pull the next bit up and then go down. And so these are the secondary waves that are transverse waves or shear waves, because everything is shaking in this direction, but the wave is propagating in the other direction, right? So the direction of propagation is perpendicular to the direction of the actual vibration. They can only travel through solids, okay? We explained that the other wave, the compression and expansion wave, can travel through anything, air, water, solid, it doesn't matter. But this can only travel through solid because if I shear something out of a solid, it's going to pull on the next bit, right? And this phenomenon creates the wave. But if I pull or if I move a mass of air or of some liquid, it's not going to pull on its neighbor. It's just going to move without any propagation. So this can only travel through solids, but rocks are solid, so they travel through rocks. And we have this reduced speed, which is why they're called secondary, because they're a little bit slower and they arrive later. But because they have this shear component and materials are normally much less stiff to bending than they are to being compressed, this results in much larger amplitudes. And are the reason, these are the destructive waves, right? When you have an earthquake, what destroys your house or your bridge or whatever, it's these secondary waves that arrive a little bit later. And they have larger amplitude because materials are less stiff in bending than in compression. And then finally, we have the surface waves that only happen in the surface. This can be very, very destructive because they can have the largest amplitude, but they don't travel very far. So it's normally a very low frequency movement, but very large movement. normally only around the epicenter of the earthquake. If you don't, here's an image of what they look like. So we have the Rayleigh wave down below, which is like the waves in the ocean. So a particle in the soil here will move in circles, right? Will go a little bit to the left and then down and then back up and move in circles like that. So of course the wave, the material is not moving, it's just the wave that is moving. And then these other waves are like sideways wave, where the earth is shaking back and forth. But you can see really clearly here that it's only these layers, like that layer and that layer and these layers that are moving. The layers below, like this one and this one, are almost not moving at all. And it's harder to see, but the same is true for the Rayleigh waves. Like a point up here, sorry, a point up here, it's going in circles of maybe that size, while a point down here, it's moving in much smaller circles, and a point down here is probably not moving at all. So those, yeah, that's what they're called surface waves, because they only affect the surface of the material. Okay. So how do we design for earthquakes? Well, one very important concept when designing a structure to resist earthquake is the ductility, okay? The ductility is some kind of measure of the amount of plastic deformation that can take place before the structure collapse. So an example of a material with very low ductility would be like something like glass, which is very stiff. Like glass is hard. It's difficult to deform. But once you deform it, it kind of explodes. It collapses. So even though it's hard, there is very little ductility in it. So it's stiff, but not ductile. Of course, an example of a material that has high ductility, a construction material is, for example, steel, which is much more like chewing gum. If you have a beam made of steel and you bend it out of shape, well, it actually goes out of shape, but it doesn't break. It doesn't break off. At least not with construction steel. Of course, there is much more. There are some kinds of steel that are very brittle. The kind of steels used for tools, for example, is much more brittle. But construction steel is ductile, and it has this ability to plastically deform without breaking. Okay, and in order, so in the 60s and 70s, for example, when people design structures for earthquake, they were just trying to do them, to make them as strong as possible meaning as stiff as possible. So just have more steel, more concrete, stiffer structures. But that turned out to be not a very good idea for reasons that we're going to be looking at later. And nowadays, the philosophy is making them more ductile. So being able to deform without collapsing. This deformation, it's often kind of fatal. So it's an ultimate limit state condition. So your structure after the earthquake will be useless because of all the deformation induced, but at least it will not collapse and it will not kill anybody. So it is better to need to rebuild your structure than in top of having to rebuild it, also having killed a few hundred people. But that's why this ductility philosophy has started to win today. Yeah, if we have this typical response of a structure, so we have a deformation in the formation on this axis and the force, the restoring force on the other axis. And at the beginning, almost all structures behave linearly. So it looks almost like a spring, right? Where we have that the force is just some constant by the displacement. But at this point, we reach yielding and we have an almost flat response, okay? And a brittle structure will fail almost immediately after yielding. A very ductile structure will fail like with a much larger deformation. I think it's time for a pause. So let's do a 15-minute pause and I'll explain why this is important or how this affects the response to an earthquake later, okay? So see you at 10:15. So, thank you, Victor. We were talking about yielding response and how and why it's important for the response of an earthquake. So, as you remember from physics, energy, it is 4 times displacement, right? So the energy in this graph, it's the area under the curve, the area under the curve that represents force and displacement. So this is all elastic energy here. And all this part here would be plastic energy, right? Because the structure is already plasticized. But so and the ground shaking in an earthquake is inputting energy into the system, making it shake more and more. But the plastic energy is not input into the system. All the plastic energy is dissipated in heat. So it's more or less just being used to heat the different components of the structure. So when a structure has a ductile response, that means it's capable of deforming without the force increasing, it means that the entire structure is acting as a damper, okay? The work of a damper is to dissipate energy, right? The energy for impact or energy from whatever other input. And with a spring, it doesn't work. If I have a spring that is fastened to something and I pull it, as soon as I release it, all that energy is going to go back into the system, right? The spring is going to snap. The same is if I have a tall building, for example, and I deform it and I release it, and if the deformation is elastic, then it's just going to snap back and continue to shake. Now, if I deform it plastically and I release it, it's just going to stay there. All that energy that I put into the deformation is not going to be transformed into vibration energy, but it's just going to be dissipated. So you can imagine an earthquake has a series of hundreds of very small of these impulses. And if you achieve plasticity, then most of them are not gonna contribute anything to the vibration, to the energy. While if the structure is very, very strong, very, very stiff, it means that whatever you do, it will not be plastic, and every single little impulse that's coming from the earthquake will result in an increased vibrational energy. So even even though your structure is very strong and very stiff, you can accumulate enough energy so that you shake it until it collapses. Okay, but this is all in the plastic or inelastic domain, right? And for the purposes of this course, we're going to limit ourselves to only elastic response, right? You have to, in the exercise, you're going to have to calculate the response to an earthquake, but all those calculations are always going to be in the elastic domain, okay? So it's just important for you to know that introducing this ductile behavior in a structure, whether it's a bridge or a building, it's in somehow the physical equivalent of converting the entire structure, or at least parts of that structure, into a damper, okay? A mechanism that is there to dissipate energy, to remove energy from the system, to break down the vibrations, instead of just, if the structure is perfectly elastic, then the vibrations during an earthquake are always increasing. So and there are special elements, special beams, for example, that you can use in a building that are designed for seismic response. So they are designed to yield and to plasticize in given spots and so on. But how to use them and how the design and simulation of those, it's a little bit above what we're going to see in this level, in this course, because we're going to limit ourselves to the elastic response. Okay. So with that being said, now I'm going to introduce the response spectrum. which is the main tool for which that engineers use when designing for earthquakes. It is the response spectrum is how the norms or the codes dictate that you should take into consideration earthquakes, at least in the US and in the Eurocode. Okay, so when a structure needs to be earthquake resistant, it has to be in the norm resistant to a specific response spectrum. Okay, so what is the response spectrum? Well, here we have, this is the graph of the accelerations induced in the ground for a given earthquake. Okay, this particular earthquake was measured in the US in the 40s, but it's not very, that is not the interesting part. We just need an example of an earthquake to use, right? And we can have, and here we have an example of a structure, okay? It has a certain stiffness, it has a certain mass, it has a certain damping ratio, right? So we can calculate the response of that specific structure to that specific earthquake, right? Nothing very complicated so far. We're just gonna simulate this particular earthquake here on this particular structure and see what happens, okay? Okay. So this is the structure that we were looking at before. We calculated, and this is the response of the structure in time, right? And we have calculated how it would shake with a simple time stepping simulation. And we have come to the result that the maximum displacement will be 12.67 inches, right? That's what we're seeing there. The book, it's in inches because it's an American book, sadly enough, but whatever, you understand. For a given structure, we can calculate the response and then just try to remember the maximum displacement. That's the important, the interesting part, the part that we want to save for later. But then we can ask ourselves, well, what would happen to a slightly different structure? Okay, what would happen, for example, if we had a structure that has the same damping ratio, but a slightly different natural period of vibration, okay? So before we had a period of vibration of half a second. That means a natural frequency of 2 hertz. And now we have a period of vibration of 1 second, which means a natural frequency of 1 hertz. What would happen to this structure? Well, this structure will have a different response, of course. It can be seen in this line. And because the structure is different, because the period of vibration is different, we will reach a different maximum displacement, more than double the previous one, right? But of course there is no reason why we should stop at this two structures, we can then ask what happened to some other structure. Again, with the same damping, but with a different period of vibration, how would this structure respond? And we can see that we can observe a different maximum displacement here. So a response spectrum, it's a curve that combines all these results. Okay, so instead of calculating the result for 2, 3, 4, 5 many structures, all of different periods of vibration, we calculate the results for like hundreds of structures so that we can create this line, right? That line represents the maximum displacement for a given earthquake for structures of different periods of vibration, okay? So in the future, if I wanted to know, okay, what would be the response, the maximum displacement to this earthquake, to this particular earthquake, if my structure had like 1.7 seconds as its natural period. Well, then I can just look it up in this curve, right? 1.7 is somewhere here, and that will give me the result. Maybe 5 inches or something like that, right? So the response spectrum, it's a way of trying to summarize or to put together all these results from all these different analyses, okay, into one single curve, okay. And we are big, of course. Relate to the frequency of the earthquake? No. This is the frequency. So there's a question in the chat. What is Tn? Tn is a natural period of vibration of the structure. Okay. So you remember the frequency of the structure is the stiffness divided by the mass, the square root of the stiffness divided by the mass, right? So the period of vibration is 1 divided by F. So what we're, all these 3 different structures have different periods of vibration. The structure, not the earthquake. The earthquake is always the same, okay? So all of them are being subject to this earthquake, okay? So it's always the same. So this is so that is the response spectrum for a given earthquake, okay? For that specific earthquake. It's not for any earthquake, it's just for that specific one. But it is, in a sense, for any structure, okay? Because any structure is going to have a natural period of vibration, and we can just look it up here in this axis where the natural period of vibration is, and read out in this other axis what the maximum response will be. Of course, it's not perfect because the maximum response is not the only interesting thing, but it is a way of reducing the amount of information needed. Thank you for the question. Yeah, exactly. So this particular spectrum is being plotted with T here, right? So we are plotting it with the period of vibration. But of course, if I wanted to, I could draw the frequency spectrum with F, and here the maximum displacement, right? The book just and also the norms, they just choose to plot it against T, but it can be plotted against the natural frequency also. It's just another curve, but it will have the same information, of course, right? But in a sense, it's trying to represent all structures, all possible structures at the same time, all right? But one thing is important, remember, this spectrum is for a given earthquake, so it's specific to that earthquake, and it's also for a given damping ratio. If I had a different damping ratio, I would have a different response. So the maximums will be different, so my curve will be somewhere else. Okay? Here are examples of real spectrums that have been measured in real earthquakes, right? You have the maximum displacement in millimeters on the y-axis, and then the period of vibration. And of course, there is no reason why you should why we should limit ourselves to the maximum displacement. Here is an example of a spectrum with the maximum speed. So as your structure shakes, there is it has some maximum displacement, but it also has some maximum speed at some point. And you can also plot that spectrum, the spectrum of speed versus the period. And you can also plot the acceleration. This is the spectrum of a maximum acceleration versus the period of the structure, okay? And as you can see, there are varying, in this, at least in this curve that I'm showing you now, maybe it's easier to see here, there are different levels of damping. So a structure with zero damping will have the black response. So the vibration is very large, while a structure that has 30% damping, which is unbelievably large for a structure, it will have a much smaller response. That is just expected, right? The higher the damping, the lower the response. More realistically for a structure would probably be the red curve with a damping ratio of 2%, maybe 5%, it's also realistic. So a real engineering structure will behave somewhere within those two. Okay. This is what Eurocode has to say about spectrum, okay? So when you design a structure according to Eurocode with respect to earthquake, the Eurocode will give you this curve, okay, that will represent, in this case, the acceleration, okay? So if you're going to design a structure and you come through your calculations that your structure has a period of, I don't know, 0.7, that will be somewhere here. So then you go to to the spectrum and read the value of the acceleration that you will have to resist. It will be maybe, I don't know, 1.1 meters per second, two, right? This spectrum is composed of 4 parts. One part which is a linear part, then we have a constant part, then we have this part which is actually like a hyperbole, I think it's called, like 1 divided by x curve. And then we have this other part which is 1 divided by x squared. But these all these 4 parts are given by these 4 equations here. I'm not going to go into these specifics, but and the values, these different values of the constants that go into the calculations are given by in this table, and then they depend on the type of soil that you're building on, right? It makes sense that different types of soil will have different responses. So once you know the type of soil that you're working, you can read the relevant values from this table. Oops. And once you input those values into these equations here, you will obtain the actual shape of your response spectrum that you have to use for designing your structure. So normally, for example, in the exam, when there is a question about earthquake, it can normally be like you will be given a spectrum that would look something similar to the Eurocode, I guess, with period and acceleration, and then you will be given a structure with some properties, and then you have to calculate you're going to have to calculate the frequency, and with the and also the period, and then you have to like look up the acceleration from the spectrum, and from then you'd have to calculate the response to that. Calculate, for example, how much deformation that this acceleration induces, or if the structure yields or doesn't yield, that kind of stuff. I'm going to jump over this. Okay. So normally, as I was showing you, we can calculate the spectrum for the deformation for D. But then there is something called the pseudo velocity and the pseudo acceleration. If you were paying attention, no, it doesn't say anything. But here, so if we have, let's say that we have a response of a structure, which is a perfect sinus wave, right? It looks exactly like this. Okay. So that this is the response U with time. Then the response will be like some amplitude times the sinus of omega t, right? This is one spectrum. Wait, there is a question now. 26. This response, did you mean the specific type of soil a certain period T? No. The period T is the period of the structure, always, right? But these curves or this part that make up this structure, they have different constants, right? They are the which define these equations, and those constants are read from this table, here, and are dependent on the type of soil. But T is always the period of the structure, okay? But it's the other constants that depend on the soil. All these constants that are here. Okay, so going back, where were we? Here. Okay. if my response was a perfect sinus, which is not going to be, but just assuming, this is going to be the displacement. Then, of course, the speed will be the derivative, right? So the speed is going to be the frequency times the cosinus of omega t, because that is the derivative. And the acceleration is going to be omega squared a minus sinus of omega t. That is the acceleration, right? That's a property of a sinus shape. That if the maximum, in this case, the U max is going to be the amplitude, of course, and the V max is going to be the amplitude times the frequency, and the acceleration max is going to be the amplitude times the frequency squared. Okay? That is just how, yeah, the trigonometric function works. Okay. Now, in reality, the response of a structure is not a perfect sinusoidal wave, but is very close to a perfect sinusoidal, particularly around the point where the response is the maximum. Okay. So if we now look at this curve here, this part is not a perfect sinus wave, but it is very close to a perfect sinus wave. So we can really, if we can approximate it by a perfect sinus wave with this amplitude, right? And it will not be too far off. So for engineering's application, it's okay to approximate it by a perfect sinus wave. So if we go back to this slide, normally we would calculate the peak deformation using this method of simulating every possible structure and putting them all together in a line. And then we would just say, okay, but then the maximum speed will just be like the maximum displacement times the frequency. And the maximum acceleration is just going to be the maximum displacement times the frequency squared, okay? So the first one is calculated. The peak deformation is an actual calculation. The peak velocity and the peak acceleration are only approximations. And that's why it's called pseudo velocity and pseudo acceleration, okay? Yes. No, this one. So if we go back to the examples that I show you of displacement, here we have the display the maximum displacement. So U. Okay. If we go to the next slide, you can see that now we have the speed, and while the displacements are quite high, even for very large periods of vibration. So even when we're talking about periods of vibration that are very large, 2 or more seconds, they're still measurable displacements. But if we look at the speed, we get that for very high values, the pseudo speed, it is almost zero always, okay? Why would that be? Well, if we look back at the equations that we had before, we have that the speed, or the maximum speed, is gonna be approximately the maximum displacement times omega, right? But omega is 2 pi divided by the period, okay, of the structure. So when t gets very, very large, then we are dividing by a very large number. And so everything is getting smaller and smaller. And that's what we see here. And if we go to, no. I'm sorry. I screwed up. Sorry, so this is the displacement. Yeah, so the displacement are large for large periods. The speed is the speed is now a little less large, and the acceleration is even less large. And it's for the same reason, right? We have that the maximum speed we said was the maximum displacement times 2 pi divided by t, and the maximum acceleration is the maximum displacement times 2 pi divided by t squared. So as t gets larger and larger, then the accelerations are going to get smaller and smaller, and also the speed, but it's much more noticeable in the accelerations because it's squared, okay? Give me. So let me try to explain this from a more pedagogical view. Like, let's imagine that we have a very slender structure, okay? So the structure is very slender. This is the boundary conditions, and we have a mass here, okay? So now we have a K that it's small, right? K small. That means that the frequency which is by this formula, it's also going to be pretty small, right? And that means that the period T is large. Because the period of vibration is 1 divided by the, or okay, 2 pi divided by the frequency. All right? So what happened when we introduce an earthquake here? Okay, we have some, the ground is moving. Well, this structure is so slender that it's gonna probably not deform a lot, right? Oh, sorry, it's going to, so the ground, when the ground shakes, it's going to move because that's an imposition. That's what we're telling the ground to do. But the structure on top is not going to move much because the structure is very flexible, right? So it doesn't have the necessary rigidity to move, to accelerate the mass back and forth. So because of that, this is going to lead to a large displacement. So the displacement is, we're measuring is this one, right? So Umax is going to be large, but Amax is going to be small. Because the mass is not accelerating, the mass is not moving, the ground is moving underneath the mass, but the mass of the structure is not moving because the structure is very flexible, okay? Now, let's try to imagine this. Let's try to do it the same size. We have the same structure, but now much stiffer, okay? It has a very stiff base or a very rigid structure, okay? Now, K is large, and so omega is also very large, and T, the period of vibration, is very small now, because T is 1 divided by omega, okay? So now when the ground shakes, like in the previous time, what's going to happen is that the structure is going to shake, it's going to move in its entirety without bending, right? It's a stiff structure, so if the ground moves, the mass on top just follows the ground perfectly, okay? So that is going to result in a U max that is very small. Remember, this U max is not, it's the deformation within the structure, it's the bending of the structure. The structure is going to move, but it's going to move in one piece, like a solid, rigid thing. So the deformation of the structure is going to be very small. Yes? And the acceleration of the mass is now going to be very large, because as the ground shakes, the mass shake with the ground. So it's actually the acceleration of the mass, it's going to be equal to the acceleration of the ground. Okay? So those are the two kind of limit cases. If we have a very slender structure, then we have this condition here. If we have a very stiff structure, then we have this condition here, right? And that is what we could see also in the plots. If I draw, for example, something like the Umax with the period of the structure, if you remember the figures, they look something like this, right? So at this point, we are with a very large period. A large period, it means a structure that takes a lot of time to move back and forth. And that means that the structure is very slender, okay? So it is, yeah. While a very short period of vibration, it means that the structure is going back and forth very quickly. And that only happens if the structure is very, very stiff. So down here, we are with a stiff structure. Okay? And that is exactly what we see when we do this consideration, right? We have a slender structure that leads to a large Umax. And here we have a stiff structure that leads to a tiny Umax, okay? But now I can draw a similar plot for the acceleration. Okay, with the periods. And they look something like this. Right? If you, both from the Eurocode, it gives you a shape like that, but also from the real examples that I show you, they look something like that. And it's, again, like we were saying, a stiff structure will be somewhere here with a large acceleration, with an acceleration that is equal to the acceleration of the ground. That is what we saw here. And a very slender structure will be somewhere over here with almost zero acceleration, okay? So as you can see in this kind of very coarse consideration, it makes a lot of sense when we then move back to these slides, right? No, sorry. We have stiff structures here with little displacement and slender structure here with very large displacement. And we have stiff structures here with very large acceleration and slender structures here with very low acceleration, right? It makes kind of perfect sense, or at least it is what we would expect of the spectrum to look. And of course, the speed spectrum looks something in between, right? So we have, here's a displacement like we expected. Here's the acceleration, also the way we expected it. And here is the speed, which looks something in between. But it's 11 o'clock now, so I guess it's time for another pause. I'm gonna just check if there were questions. Are the earthquakes generally similar locally? Okay, I'll answer the question after the pause, okay? So it is 11:02, so see you at 11:17, okay? All right, so there was a question about if earthquakes, and how similar are earthquakes that happen in the same place, and how does the spectrum, the design spectrum cover for that? And let's try to answer that question before I continue. So for a given earthquake, if you calculate the spectrum for that earthquake, it's going to be, let's say that we calculate the acceleration spectrum, right? It's going to be quite spiky. So it's going to look something like this, right? Because it depends on lots of details of the specific, the location of the earthquake and so on, the type of rock underneath. But what people have done to create the design spectrum is that you compute all the spectrum of all the largest earthquakes for a given region and plot them all in the same kind of graph, just on top of each other. Okay, and then you say, okay, the design spectrum here is going to be something like this. So from a number of earthquakes, you do some kind of statistical analysis so that your design spectrum cover most of the cases. Okay, the whole thing is probabilistic. So of course there can be, if you can be like very unlucky and just be at the perfect frequency and have the perfect earthquake so that the response is larger than the spectrum, but that is supposed to be unlikely. So the yellow curve is designed to cover most of the earthquakes and for most of the frequencies. Okay. Yeah. Again, so different earthquakes can look very differently, but by considering the worst historically recorded earthquake together, you can arrive at a design spectrum that more or less covers all of them, right? Okay. This is a slide of how the American code gives the design spectrum. Okay, and there are two things to notice, or two important things to notice. One is that it is the velocity spectrum. So the Eurocode will give the the acceleration spectrum. In the American, it's the velocity spectrum. And second is that the scale is logarithmic, okay? The European norm gives linear scale. The American gives a logarithmic scale. Why they give a logarithmic scale? Well, the answer is that in a logarithmic scale, you can read all three quantities at the same time: displacement, speed, and acceleration. It's a little bit messy, but it works. So for example, let's say that we have a frequency with a natural period of, I don't know, 1.5 seconds, and that we had a damping ratio of 2%, okay? Then for this given earthquake, we can find our 1.5 seconds, that is here, right? And these different curves, the different curves here represent the different levels of damping. And you can see here in the legend, we have 0% damping, 2% damping, 5, 10, and 20. So the 2% damping, which is the one we're interested in, is the second highest curve, right? Because the lower the damping, the higher the response. So I just draw a line here. And I arrive at that point. Okay? So I would obtain that my Vmax, the maximum speed, is going to be something like 30 inches per second, right? If I read out this value here. Remember, the scale is logarithmic, so. But so how do I get the maximum displacement and the maximum acceleration? Well, you can see here we have the maximum displacement in this very strange diagonal axis, and the maximum acceleration in this very strange diagonal axis on the other diagonal. So if I read these values diagonally like this, then I would arrive at a maximum acceleration of 0.21 g. Okay, and if I now read this value following the other diagonal, I will achieve a maximum displacement of 5 inches. Okay. And again, like, it should be the case that that the speed 30 inches per second, it's more or less equal to the displacement 5 inches times omega square, right? That is 2I t squared. No, sorry, not squared, because it's the speed. The speed is the displacement times the frequency. Okay, so if you put this to 1.5, it should more or less turn out to be the case. Okay, so this plot again, this is the actual response for an earthquake. Amax is ground acceleration. No, Amax is the maximum acceleration experienced by the structure. Okay, so what we're calculating here is the maximum displacement, the maximum velocity, and the maximum acceleration experienced by the mass of the structure. Yes. And this is, again, this is the response for a given earthquake. Okay, we're still talking about the same earthquake that happened in the 40s that we were talking from the beginning, and that's why you can see the response is very spiky, because the results varies a lot. It's very sensitive to the period. While of course the norm will not give you this kind of curves with so many spikes. It will probably say something like, yeah, you should consider something like this, right? Some kind of envelope that covers all possible earthquakes for a given region, or all likely earthquakes for a given region. All right. This is again the same graph, but here we can notice something. If I draw in this graph the ground acceleration, if someone were asking me about the ground acceleration, it will be here, right? This is the maximum acceleration of the ground. And we can, of course, this line, this line continues here. The maximum acceleration of the ground is constant. But we can see that for very small, I mean, as the period gets smaller and smaller, so we're going in this direction, the structure is getting stiffer and stiffer, right? And we observed before that for a very stiff structure, the acceleration of the structure is going to be very close to the actual acceleration of the ground, right? Because the structure will move as a solid object. So the mass of the structure is going to move together with the ground, okay? And that's what we see here. All these curves, they tend to go towards this line, which is the line of the acceleration of the ground. So for very stiff structures, the acceleration of the structure tends to go towards the acceleration of the ground, while the opposite is true of very slender structure. Okay. As the period gets larger and larger, that means that our structures are getting more and more slender. And as we can see, all the lines tend to go towards the displacement of the structure being equal to the displacement of the ground. Just as we discussed before, the ground is moving, but the mass of the structure is not moving because the structure it doesn't have enough stiffness to accelerate the mass. So the ground is moving. So if the ground moves 1 meter, then the structure will bend 1 meter. If the ground moves half a meter, then the structure will bend half a meter. And that is just to corroborate what we explained before. In stiffer structure, A max equal A ground. In slender structure, B max equals D ground. But of course, in reality, most structures will be somewhere in between, and we have these very complicated responses that are varying. Yes. In when we calculate there's a question in the chat. Could you please repeat why the pseudo acceleration and the pseudo velocity are pseudo? Well, so to calculate the spectrum, we calculate Here, like D max for each T, right? We actually have to simulate every single possible period of vibration. We have to simulate it for a rather long period of time. And then from that very long period of time, we save the maximum value. We save the maximum displacement, whatever that was. Okay. We could do the same thing for the maximum speed and for the maximum acceleration, but we don't. We approximate. Okay? And we approximate. So the displacement spectrum is calculated and is the actual maximum displacement. So it is there is no pseudo in front of the displacement spectrum. But the speed spectrum and the acceleration spectrum are not calculated. They're not the actual maximum speed and maximum acceleration response of the structure. It is just an approximation done with these equations, which is good enough. And that's why we put a pseudo in front of it. Yes. All right. And this is what I was talking before. The American norm will give an spectrum that is not as spiky as this one, which is a response to a real spectrum. It's just flat. But it is meant to cover all likely earthquake in that area. Of course, it varies with the area that we're talking about. So you need these values. The values A, B, C, D, E, and F are given, but then the values of alpha A, alpha B, and alpha D will be different for each region. Okay, for depending what region you are simulating, and the idea is that hopefully, if we have an earthquake in that region, it will be somewhere here, right? So that the probability of having something like this is very low. So we don't want that to happen. Okay. Okay, so there is another question now. Why U is measured at the ground level, but A is measured at the mass of the structure. So this structure that I've been drawing all the time is the simplest possible structure, right? It's like a 1 degree of freedom and all the mass is concentrated in one point. Structure in reality is not going to be like that. The structure is going to have a modal response of different shapes. For example, if we're talking about a bridge, it will bend like this. Okay. or a building or whatever. So it is an oversimplification what I'm doing. But thing is, why the displacement that we want to obtain is the deformation of the structure, okay? Because we want to calculate, for example, the bending moments or the shear forces inside our structure, right? And those come from the deformation of the structure. That's why if our entire building if we have this case scenario where the entire building move maybe 1 meter to the left, then we want the U to be 0 because the building is not bent. Our structure has not been bent. And because it has not been bent, it has not deformed, it has just moved as a single solid, then there are no internal forces, okay? Our beam is not subjected to any moment. There are no shear forces. Everything just moved to the side, okay? And so we want, what we're really interested in are the bending moment and shear forces. But those, of course, are going to be depending on the deformation, right? Maybe I could even do this. Like from okay, so the forces applying to our structure are the stiffness matrix of the structure times the deformation. So that's why we're interested in the deformation of the structure. We're not interested in how much it moved as a single piece, but we're interested in how much it deformed, okay? So that's why if the ground moves, but not the mass of the structure, well, then our structure is being deformed. And we want to obtain a measurement of that deformation, okay? On the other hand, we have this other equation also. Okay, where the forces are going to be proportional to the acceleration of the mass. Okay, so if we have this other scenario, where the ground is moving but the mass is not moving, then even though the ground is accelerating, we're interested only in the acceleration of the mass. So this acceleration should be 0 because it is the acceleration of the mass that is going to induce forces, okay? So the U is always relative. The displacement, it's a relative quantity, okay? A point in space does not have a displacement. That it's now when we have two different points in a structure, we can start talking about their relative displacement. If they are stretched or compressed, but if they move together, the relative displacement of them is 0. Okay, so displacement is always a relative term. It's always when we're talking about one part of the structure in relation to the other part of the structure. And that's what creates bending moments, that's what creates normal forces, that's what creates stresses. While acceleration, it is an absolute quantity, okay? It makes perfect sense of talking about the acceleration of one point. If you put an accelerometer in that point, you can measure its acceleration. While if you have a ruler to measure displacement, you cannot put it on the point. You have to have a reference point always. So displacement, it's a relative quantity. It's always displacement with respect to something else. And that's why we measure it in the difference in displacement. The displacement of one point compared to the displacement of the other point. And that represents the deformation of the structure. And we are interested in the deformation because it's that deformation that will induce moments, forces, stresses, strains in our structure. The acceleration is not a relative quantity, it's an absolute quantity. And in that case, we are interested in the acceleration of each mass of the structure. Of course, in this drawing that I made, it's a very simple where all the mass is in one point. In reality, we would like to know the mass, the accelerations and the deformations in all the points, but I was just simplifying. In reality, you would what you would do is you would do a modal analysis, right? You have a structure with hundreds of degrees of freedom. So you do a modal analysis so that you end up with each modal stiffness, modal mass, modal displacement, and modal acceleration. And you look at each mode on itself. Yeah, but displacement is always relative, it's always the deformation, while acceleration is always the acceleration of a given mass. I hope that answered the question. Well, here we have a simple example, again, of a very simple structure with some quantities, a mass, a stiffness, and a damping ratio. With the mass and stiffness, we can calculate frequency, natural frequency, and from the natural frequency, we can easily obtain the natural period of vibration. And once I have that period of vibration, I can input it in my design spectrum and obtain the different values for the velocities, the displacement, and the accelerations. Okay, but normally we're not interested in the displacement, but again, like I said before, we're interested in for example, the bending moment of a given beam. So once we have obtained the displacement, we use the stiffness K of the structure to calculate in this case, the bending moment. Could have been the shear force or anything, right? So we know for a given, like the beam is going to deform like this. Yeah, probably not. Doesn't deform like this. Right. And we can, given that we know all the properties of this beam, we have the stiffness there and the length also. We can easily calculate how the bending diagram looks like, right? And by doing that, we can calculate the equivalent static force, right? So when we built this structure, we will need to build it with an element, with a beam that can withstand at least this many kilonewtons per meter of moment, right? So that it will survive the earthquake elastically without ever being plasticized. And this is this is a good example for why just making a structure stiffer is not always a good idea. Okay? Because what happens if let's say that I make the structure double as stiff. Okay, so now it has 2K. Okay. because it has double the stiffness, now the frequency is going to go up. So the frequency now is, the new frequency is going to be the square root of 2, right? Now we have a 2 in there, in the square root. So the frequency is going to be the square root of 2 times what it was before, which is 1.7 something, the old stiffness. It is 1.7, right? Yeah, I think so. And so now the period is going to be slightly lower. I'm guessing here, I don't have a calculator, but if it was 2 seconds, maybe it's going to be 3 seconds, let's say. That's the new period. Okay? So now I'm going to have to read my values from here, 1.3 instead of 2. And then I go up there. And then I go down here. And I get a new displacement. Okay? I had a that line was not there. Something like that will be more realistic. So before we had a displacement of 7.47, now the displacement will be maybe 5. Okay. Okay, but before I had this is k times 7.47, right? But now we have to do 2k times 5 because our structure has been doubled, the stiffness has been doubled. So making a stiffer structure will actually lead to a much larger moment. I don't know how much this would be. But we are reducing the displacement from 7 to 5, which is not half, it's more than half, while we're doubling the structure. So if I make that structure stiffer, I'm going to end up with higher bending moments. So it's not obvious that just by making it stiffer is going to be better for the structure. Sometimes the optimal thing to do for the point of view of an earthquake resistance is to make it less stiff. It depends a lot. So of course, if I make it like, so you know, every time I make it stiffer, I'm walking in this direction, right, in the curve. If I make it so stiff that the displacement goes down to almost nothing, well, this displacement will be closer and closer to 0, but these are getting closer and closer to infinity. So it's not obvious that making it stiffer will reduce the bending moments or reduce the internal stresses in the structure. Well, that's all I had. So I don't know. Are there more questions? Well, no more questions apparently. So, well, thank you very much for attending. Okay. Why are you using the? Well, they have you have all the questions from the previous year, right? All the exams are available, so you can look them up. Normally, you'll be given some kind of acceleration spectrum and the properties of some structure, and then you just have to, with this, calculate the frequencies, the response, the periods, and then just look it up look up in the diagram what that means for the cellular acceleration and for the displacement, and from there calculate maybe some bending moment or something like that. it's always something like that. So it's going to be similar to this problem, maybe a little bit more complicated with a little bit more details, but it's something like this. You're giving the characteristic of a structure, you're giving a spectrum, and you have to calculate stresses or bending moments or something like that. So we can get, no. This is just an example that I took from the book, but normally the plot will be the Eurocode version. But I don't know, maybe, who knows? Maybe they change it up and you get the American plot. But it just never happened, I don't think. But it could happen. I mean, it's not much more difficult. I must, someone is asking me if what n is in slide 26. And I must admit that I don't remember. So I can't help you there. You're going to have to look up the Eurocode. I have no idea what this type of soils are and so on. Or this, I think that might be the damping. But the answer is I don't know. Someone's asking for hints for exercise in real structure with K matrix. So there should be like a printout which is hints for the exercise C2. That should be available from Canvas, I think, on how to use it. Then in a real structure where K is a matrix, how are these spectra used? Well, then you have to look at each modal response by itself. Okay, so if you have K as a matrix, then you have to decompose it using the modal decomposition into a bunch of modal stiffnesses and a bunch of modal masses. And then for each one of them, you'd have to calculate a period and a response, right? That's how it's done for a structure with more degrees of freedom. How do we find the modal damping ratio? The answer is nobody knows. Like there are hundreds of theories about the modal damping ratio and things that you can do to measure it if you have a structure. But normally, at least for bridges, which is the area in which I work, it's given by the norm. If you have a concrete structure, then you are allowed to assume a modal damping ratio of 2%. If you have a steel structure, then you have to assume a modal damping ratio of 1%. So it's just dictated by the code. Even though there are ways of measuring, and if you measure it, you normally get a much higher value than the code is saying, because the code has to be on the safe side all the time, so it gives a very low value. But yeah, but if you're building a new structure or designing a new structure, then you cannot measure it on the new structure. You just have to assume whatever is written by the code. I don't have access to the canvas, but I don't know. Do you have this sheet available? The one with how to calculate the how to redo the ground acceleration to forces in each of the degrees of freedom of the structure? Maybe, maybe not. Anyhow, the the assistants should know how to do it. I mean, should have all the tips. All right, that's it for me. Thank you very much, and have a good afternoon, I guess.